This week we're going to look at the least absolute deviations method of linear regression. This is often referred to as the LAD method. Now, linear regression is a process where we best fit a line through a set of data points. And this notion of best fit has many different meanings. Some of you in the class may have seen the least squared method of linear regression, and the method we're going to look at today is a variation of that. The idea is we have a number of points in the plane represented by these little black dots, and these are particular values. These are the y values, particular y values of some thing which is being measured for different x values. So x here could be time, or it could be, for instance, different things that are being sampled, and here are your corresponding y values, and the idea is to draw the best line you can through the data points. And in the least squared method, you minimize the sum of the squares of the distances of the points to the line. And in the LAD method, you minimize simply the sum of the distances to the line. In other words, the sum of the absolute value of the differences of the y values between the given data points and the corresponding point on the line going vertically. So this, you notice straight away, this is a little bit similar to the way that the mean of a given set of real numbers is the point which minimizes the sum of the squares of the distances, and the median is the point which minimizes the sum of the absolute values. So in the same way that you have that relationship, you also have the relationship between the least squared linear regression and the LAD linear regression methods. So the LAD method is similar to the median, and the least squared method is similar to the mean. And in the same way that the median could be written as a linear programming problem, the LAD linear regression problem can also be written as a linear programming problem. So the idea is to minimize a sum of these distances, and the idea that these numbers are absolute value are represented by two inequalities. So here, Z1 up to Zn are the n absolute values, and each one of them is greater than or equal to the thing inside the absolute value and minus that thing. Now we've got n of these pairs, so we've got two n inequalities. So if we've got n points we're trying to draw a line through, there'll be n plus 2 decision variables, and we'll have the decision variables being, well, the thing that we're looking for the equation of the line, so we're looking for a and b. The line is y equals ax plus b. We're looking for a and b, but we also have these unknown variables z. We're not particularly interested in per se, but they intervene in the problem. So we have n plus 2 decision variables, we'll have 2n slack variables, we'll have n artificial variables, so we'll have a total of 4n plus 2 variables. So for instance, for 5 data points, we'll need 22 variables. So you're not going to get a problem of that magnitude to do by linear programming, but certainly this can be done by linear programming. And you might be asked on occasion to set up a linear programming problem corresponding to a certain LAD linear regression problem. There is another approach. In the same way as for the median, you can solve it using linear programming, or you can simply solve it by putting your numbers in order, in a natural order, and then the median is just the one in the middle. And this idea that the median is the one in the middle gives us this theorem here. The details are explained in the printed notes. The idea is that if you've got n data points in the plane, then the solution to the LAD problem is attained by a line that passes through two of the data points, at least two, and moreover, this line must split the points so that there's half above and half below. Now, half above and half below, you have to be a little bit careful. You've got to take into account the ones that are actually on the line. So if A represents the number of points that are either on or above, and B are the set of points which are on or below, then A and B must both be at least half the number of points. So this enables us to solve the LAD problem geometrically provided you've got a small number of data points. You can just look at the possible lines that you need to consider and find the one which gives you the best value. Here's an example of a geometric solution. You're given 5 data points. You can see here straight away 4 of them actually lie on a line, and the 5th one is off the line. So if we're going to use the theorem on the previous slide, we need to consider lines that go through 2 of the points. So there are 5 such lines. So in obvious notation, P1, P5, that's the line through P1 and P5. P2, P5, P3, P5, P4, P5, and the line that goes through these 4 points here, P1, P2, P3, P4. Now, P1, P5 and P4, P5 don't satisfy the theorem. For instance, if you look at P1, P5, the line through P1 and P5, then the points which are on or above it are just P1 and P5. So there's only 2 of those, and that's not half of 5. So that's not more than half of 5. So P1, P5 can be excluded, and P4, P5 can be, it's this line here, can be excluded by the same reasoning. And so there's just 3 lines to consider. And so you just do them one at a time. For P2, P5, you draw the line in this one here. You need to find the equation of that line, which you can easily write down because you've got 2 points that it goes through. And then for that equation, you calculate the sum of the differences, the distances from the points to the line. And you add that up. I won't do the calculation here. It'll take you a line or two to add up all the points, but the answer in this particular case is 4/3. And for the other 2 cases, you get 2 and 1. So we're looking for the smallest one, so the smallest one is the last one. So the solution to the LAD regression problem is the line P1, P2, P3, P4, and that just happens to be the line y equals x, and that's the solution. So you can see that in this LAD linear regression situation, you can have cases where you're asked to set up the problem as a linear programming problem, but you'd only be asked to solve it using linear programming for a very small number of points. Alternatively, you could be given more points and you're asked to solve it using this, well, it's effectively a geometric solution by looking at all the relevant lines and computing the sums and seeing which one is the smallest.